Unit 12, Oxidation Reduction, Lecture 1. In this unit, we're going to talk about some important terms, how the concept of oxidation and reduction, the terms, came about. We'll talk about how to assign oxidation numbers in a consistent manner. Then we'll get into balancing equations, and we will do this first by the half-cell method, then by the change in oxidation number method. We will take what we know about stoichiometry and bring into that the concept of oxidation reduction. We'll talk about oxidizing agents and reducing agents and how to figure out what things might change to. And we will wrap it up on voltaic cells. Some terms. Look, folks. Students always fuss because they say, well, the terms oxidation reduction are backwards. Well, not if you look at a little bit about the way the thing evolved. Look at this equation, cupric oxide plus hydrogen producing copper and water. Now, what happens to cupric oxide? Well, cupric oxide is reduced. What? Yeah, it lost oxygen. So the quantity of oxygen in cupric oxide is reduced. It lost oxygen. Well, what about hydrogen? Well, hydrogen is oxidized. What do we mean? Hey, folks, it gained oxygen. Cupric oxide is reduced. It lost oxygen. Hydrogen is oxidized. It gained oxygen. Yeah, makes perfect sense, doesn't it? Until you get to an equation like this. Cupric sulfide plus hydrogen gives you copper and hydrogen sulfide. Now it's the same general type of reaction, the same general appearance, except our definitions won't work here. Why? There's no oxygen involved in this. So we need to look at a more inclusive method of dealing with the concept of oxidation and reduction. And we're going to look at changes in oxidation numbers. All right, let's start with this top equation. Let's assign oxidation numbers. Well, in that top equation, the copper is a +2 and the oxygen is a -2. Copper's a +2, oxygen's a -2. Okay. And hydrogen, what's hydrogen? Hydrogen is 0. Why is it 0? It's not bonded to anything. It hasn't reacted with anything at this point. And that's going to produce copper. Here copper is as an atom. It's not bonded to anything. It doesn't have a charge. It's 0. And water, what about the charges in water? Well, hydrogen is a +1 and oxygen is a -2. Now, see what happens here. Copper goes from a +2 to a 0. It changes from a +2 to a 0. So the copper gained electrons. Got that? The copper gained electrons. It is reduced. Remember, that was from our previous life. It's reduced. It lost oxygen. But don't look at it that way now. It gains electrons, so it is reduced. And I'll give you an easy way to think about it in just a few minutes. Hydrogen goes from a 0 to a +1. So the hydrogen lost electrons. The hydrogen lost electrons. It is oxidized. It is oxidized. Now stay with that, and let's look at this next equation. Let's assign the oxidation numbers, just like we did before. Yeah. And what happens? Well, the copper goes from a +2 to a 0, just like it did before. So the copper in the cupric sulfide gains electrons. It is reduced. No oxygen in sight. And what about hydrogen? Well, hydrogen goes from a 0 to a +1, and in the process it loses electrons. It is oxidized. It is oxidized. So this is going to bring us then to the modern definitions that we are going to use. But I wanted you to see how these definitions might have come about. Here we go. Oxidation is the loss of electrons. Just learn it. Reduction is the gain of electrons. An oxidizing agent, and this is an important term, an oxidizing agent is the substance that gains electrons. An oxidizing agent is the substance that gains electrons. How does that relate to reduction? Well, the oxidizing agent is reduced. Why? Because it gains electrons. And the reducing agent is a substance that loses electrons. The reducing agent is the substance that loses electrons. Now, folks, you've got to get these four definitions straight. I don't care how you do it. Well, as long as it's honest, you understand. What I always did was memorize the easiest one. Reducing agents lose electrons. And then I figured everything else out from there. The reducing agent is a substance that's losing electrons. The reducing agent undergoes oxidation. It's an oxidation that you lose electrons. The reducing agent loses electrons. The oxidizing agent gains electrons. The oxidizing agent undergoes reduction so that it can oxidize something else. So the oxidizing agent gains electrons so that it can take it away from something else, therefore oxidize something else. Oh well. Learn it however you will. But remember these four definitions. Well, we're going to visit this again later. But first, let's get to the first item, and that is we need to assign oxidation numbers. Here's how we do it. For neutral atoms or molecules, the sum of the oxidation numbers is 0. Okay, that makes sense. For polyatomic ions, though, the sum of the oxidation numbers is whatever the charge is on that polyatomic ion. For example, nitrate, NO3 -1, the charge on that, the net charge, has got to be a -1. So you add up the charges of the others, and it better equal a -1. For sulfate, it's got to be a -2. For ammonium, it's got to be +1, for example. Oxygen is -2 in most compounds. The rare exceptions are in those 3 peroxides that you know in which oxygen has a -1, and in the couple of superoxides that you know in which oxygen has a charge of -1/2. Otherwise, oxygen is a -2. Well, there is one more exception. Fluorine is the most electronegative element, so that if oxygen is with fluorine, fluorine gets the negative charge. There's more. Fluorine always has an oxidation number of -1. This is one of the few occasions in which you'll see us using the word always in chemistry. And the other halogens are -1, except when they're bonded to oxygen. Then they're going to take on one of their positive charges, but we'll get there. Assign nitrogen an oxidation number of -3 whenever it's bonded to either carbon or hydrogen. For example, nitrogen in cyanide or nitrogen in ammonia. Assign it an oxidation number of -3. For polyatomic ions, the sum of the oxidation numbers is the net charge on the polyatomic ion. Haven't we said that before? For example, with nitrate, it'd be -1. With sulfate, -2. With ammonium, it'd be +1. Well, hey, there's more yet. If there's a third element, expect its oxidation state to accommodate the other two. For example, potassium dichromate. You can expect the chromium, which is the one in the middle, to adjust to the other two, to accommodate the other two. Fractions may occur. Remember, we're not necessarily talking about fractions of electrons. This is really just an accounting system. And fractions will always calculate out to be whole numbers before the whole thing is through. You'll see. As a rule, we write the more positive element on the left and the more negative element on the right. Okay. Let's start with an example. Here is potassium permanganate. Let's assign oxidation numbers. I suggest you start with what you're pretty confident of, and that's oxygen. Oxygen is a -2. It's not with fluorine, is it? This certainly doesn't look like a peroxide or a superoxide, so start with oxygen. It's -2. There are 4 of them, which gives you a total of -8. Now, let's go to the other thing that we know with confidence, and that's potassium. Potassium is a +1. There's only 1 of them, so you get a total of +1 from potassium. Now, manganese has to be something to make this whole thing equal 0. What does manganese have to be? Well, manganese has to be a total of +7. How many manganese are there? There's only 1. So it is a +7. And that is within the oxidation state range that we talked about of manganese back earlier when we were talking about ranges of oxidation states. All right, let's try another one. Here's the arsenate radical. The arsenate radical has a net charge of -3. Start with what you know, which is oxygen. It's a -2. There are 4 of them, giving you a total of -8. Now, there is no positive one in here, no third element in here to like potassium or sodium or something. So ask yourself, what does arsenic have to be to go with a -8 to equal -3? And the answer is +5. So arsenic in this one then is +5. Got the idea? Let's look at cupric dichromate. All right, where do we start? Good. With oxygen, of course, -2. 7 of them gives you a -14. And then you say, okay, now if you weren't sure of what the oxidation state of copper is, then look at it like this. This whole dichromate thing, you know because you know your oxidation states, you know that whole thing is a -2. If that is a -2, then copper has to be +2. Okay, copper has to be +2 because there's only one dichromate. It's a -2, so copper has to be +2. There's only one copper, so it's a +2. Now calculate chromium. What does chromium have to be to go with that +2 and that -14 to equal 0? Well, it's got to be a +12. How many chromiums do you have? You have 2. So each one is +6. Now you may need to back this up and run that back again. But let's try another example. Here's Pb3O4. Okay, where do you begin? Oh, you know, oxygen, -2. 4 of them gives you a total of -8. So what does lead have to be to go with a -8 to equal 0? And the answer is +8. But there are 3 of them. Yeah. So each one has to be 8/3 or 2 2/3. But you see there are 3 leads. There are 3 leads. So 3 times 2 2/3 happens to be +8, doesn't it? So the fraction isn't going to hurt anything. It's a bookkeeping technique. And it could be that we have a mixture of 2 different kinds of lead ions in there or something. But anyway, bookkeep it. 2 2/3. That's what it is. Oh, these should be a good exercise. Let's start up here with the sulfate of this tin. Now, start with oxygen. Oxygen's a negative 2. There are 4 times 2 is 8 oxygens, giving us a total of negative 16. What does sulfur have to be? Well, I don't know what sulfur has to be until I know what tin has to be. So let me show you how to figure that. Remember, sulfate overall, that polyatomic ion, is a negative 2, and there are 2 of them. That means that the polyatomic ion is giving us a total of negative 4. So tin has to give us a total of positive 4, and there's only 1, so it must be a positive 4. See how to work that? Let's get rid of this now. So we have tin with a positive 4. We ask ourselves, what does sulfur have to be to go with a positive 4 and a negative 16 to equal 0? And the answer is, it has to be a positive 12. There are 2 of them. Remember that 2 right there. So each sulfur must be a positive 6. Or you can write it 6 positive, whichever way is more convenient. Let's go down now and look at this one down here, ammonium dichromate. You know where to start. Start with oxygen. Oxygen is a negative 2. Their 7 gives us a total of negative 14. Well, we can't determine what chromium is until we see how much the ammonium is contributing. Well, the ammonium polyatomic ion, or the ammonium radical, is a +1, and there are 2 of them. So this gives us a total of +2 from here. So we have a +2 from ammonium, we have something from chromium, and we have a negative 14 from oxygen. So it looks to me like the chromium's got to be a total of +12. There are 2 of them, so each chromium then must be a +6. Now, do you remember how to figure the ammonium? Well, let's pull it off to the side. I'm just going to pull it off over here. You remember ammonium is a +1 overall. Nitrogen, when it is with hydrogen and carbon, should be given a negative 3. So if nitrogen is a negative 3, what does hydrogen have to be total to give you a +1? And the answer is it's got to be a +4. So each hydrogen then is a +1. So we have a negative 3 here, a +1 here, and folks, the job is done. Look at this equation. Let's determine what is oxidized and what is reduced in this equation. What's the first thing that we do? We assign the oxidation numbers to everything. Well, a lot of the stuff already has oxidation numbers on it. Isn't that convenient? For example, the Fe is already a +2. So let's go to the permanganate. The oxygen is the negative 2. There are 4 of them, gives you a total of negative 8. What does manganese have to be to go with that negative 8 to be negative 1? And it is +7. Okay. The hydrogen already has its charge. There it is, +1. The Fe is a +3. The manganese is a +2. Oh, we got to do water. How do you do it? Oxygen's negative 2. So the hydrogen has to be a total of +2. There are 2 of them, so each one is a +1. So now we have oxidation numbers assigned to everything. Now let's determine the electrons lost and gained, or what is losing electrons and what is gaining electrons. Well, the first thing that we see changing, or you may notice whatever, is iron is going from a +2 to a +3. What is it doing electron-wise? It loses electrons. It is oxidized. Now, just to keep you as a reminder, it is the reducing agent. Remember, reducing agents lose electrons. Reducing agents are oxidized. Say it again and again until it becomes absolutely clear to you. Now let's look at manganese. Manganese goes from a +7 to a +2. In the process, it gains electrons. It is reduced. It is an oxidizing agent. Oxidizing agents are reduced. Oxidizing agents gain electrons. Got the idea? Good. We're ready to start balancing by the half-cell method. Now, an oxidation reduction reaction has two half cells. It has an oxidation half cell in which electrons are lost, and it has a reduction half cell in which electrons are gained. Now, it's possible to have two oxidation reduction reactions going on at the same time, but we're not going to deal with that. Right now, we're dealing strictly with an oxidation half cell and a reduction half cell. And the important thing to remember is electrons lost equal electrons gained. The two parts of the reaction may occur independently just as long as you have a way for electrons to flow between the half cells. Let me show you. Let's look at a complete circuit that might occur in a dry cell battery. Here you have a dry cell battery. This is the carbon rod that goes down through the center of the battery. Reduction occurs here. The battery is encased in a zinc cylinder, and oxidation occurs here. Now, when you get into a separate unit, a different unit in the next course, the College Chemistry 2, we will do a more in-depth study on the dry cell battery. But right now, we'll just give you a little introduction to it. If you have a calculator or something like that, you can hook this whole process up so that electrons flow into the calculator, through the calculator, and out and back. Get the idea? Now, balancing by the half-cell method involves three fundamental steps. First, you divide the reaction, the overall reaction, into oxidation and reduction half cells. Then you balance each one of those half cells independently, and then you add the half cells. Well, we'll show you in detail. Here it is in a stepwise process. Let's start with copper and the nitrate ion producing the cupric ion and nitric oxide in an acid medium. Now, it's really important that we tell you whether it's in an acid medium or a basic medium, or a neutral, because you're going to have to use that knowledge in the balancing process. And what you're going to do is literally balance the reaction and complete it at the same time. Let's start with that nitrate ion. So we're going to write the substance being oxidized or reduced and its product. It doesn't matter which half cell you start with. We're going to start with the nitrate. So here we go. The nitrate ion goes to nitric oxide. Okay, that's the first thing. Now, we get the numbers in here. Nitrogen is going from a +5 to a +2. Oxygen isn't changing. The nitrogen is going from a +5 to a +2. What happens to it? Well, it's going to be gaining electrons, and we note the electrons gained on the left and electrons lost on the right. In this case, it happens to be gaining 3 electrons. So there they are. It's gained 3 electrons. By the way, you will notice I got rid of the charges above the nitrogens, because if you leave them up there, when you start trying to figure out the net charges, you're going to get confused if you leave those up there. So I just scribbled those up there just to be able to talk about what was losing and what was gaining. 3 electrons, yeah. Now we're going to balance the charges. We balance the charges using hydrogen ions if it's in an acid, hydroxide ions if it happened to be in a base, or whatever ions were not being involved in changing their oxidation states if we had a neutral solution. We'll get there. This is going to become clear. Just get it down. All right. This has 3 electrons plus nitrate, giving nitric oxide. The total charge on the left right now is a -4, and on the right is a 0. And the only thing we have to use to balance it, since it's in an acid medium, is hydrogen ions. So how many hydrogen ions do we add, and to which side do we add them? Well, hydrogen ions are positive. We've got -4 over there on the left. We've got to neutralize those charges, so we're going to add 4 hydrogen ions. Well, now look, our charges are balanced. 4 hydrogen ions plus 3 electrons plus nitrate, charge-wise, is 0, just like the right-hand side is. But wait a minute. We're not balanced yet. We've got oxygens in here, and we've got hydrogens. What do we do here? You balance the oxygen using water. We have 3 oxygens on the left, 1 oxygen on the right. So that means 2 oxygens unaccounted for, so we need 2 water molecules. And oh look, the hydrogen's balanced. Now, check to see if the half cell is balanced. I'll pause here, or you can hit the pause button on your video or your computer or whatever, and stop this thing and get these notes down. Now we're ready for the other half cell. So let's repeat the process with the other half cell. Here we go. Copper going to copper ion. Note the electrons lost on the right or gained on the left. Well, in this case, copper went from 0 to +2, so it lost 2 electrons. There they are. Okay, now what do? Remember, we balance the charges using hydrogen ion in acid solution, hydroxide ion if we happen to have a base, or whatever we can dig out if we are in a neutral solution. I'll show you. But this right here has the charges already balanced. Oh, good. So just leave it like it is. Balance oxygen using water. But there's not any oxygen. Good. Then you don't have to do it. So guess what? That half cell's done. Now we're ready to go to the next step. We have to make electrons lost equal to electrons gained. Now, folks, in the first half cell, you have 3 electrons gained. In the second half cell, you have 2 electrons lost. To make the electrons gained equal the electrons lost, we're going to multiply the top equation by 2. Why? That's to get us to 6. Why do we want 6? Because 6 is the least common multiple of 3 and 2. Okay. Multiply that by 2. Multiply this one by what? Sure, by 3. Got it? Okay. Now we're going to add the half cells algebraically. You know the rules of adding equations in algebra. So let's see, what do we have here? We have 2 times 4 is 8 hydrogens. We have 6 electrons in and 6 electrons out, so they go away. We have 2 nitrates. Okay, still on the reactant side, we have 3 coppers, and that's going to produce 2 NOs and 4 waters and 3 cupric ions. Yeah, see? It's completed and balanced. All right, got the idea? Just keep those rules very clearly in your head. It's actually a very logical progression of activity when you have a handle on what's going on. Well, let's do one using a basic solution. Step-by-step in a base is very similar to step-by-step in an acid, but there are some significant differences. All right, let's walk it through. You can choose either one of the half cells. It doesn't matter which one you want, but you need to choose one of them. So, whichever one, I'm going to use this one. I'm going to use the nitrite ion going to the nitrate ion. Now, note electrons lost on the right or electrons gained on the left, whatever the case may be. Well, this is going with nitrogen from a +3 to nitrogen at a +5. So what's it doing? Well, it's losing 2 electrons. So we write the electrons lost on the right. Think about it, and it will make sense. All right, Now we balance the charges using hydrogen ion if it's an acid, but it isn't, it's in base. So we use hydroxide ion. We'll come to the neutral solutions in a minute. So we're going to use hydroxide ions to balance the charge. Now what's the charge? Well, on the left the charge is a -1. On the right the charge is a -3. So we have to pick up 2 more negative charges on the left. So we use 2 hydroxide ions. Now the charges are balanced. All right, what's next? Balance oxygen using water. How many oxygens do you have on the left? Well, let's see. We have 2 from hydroxide and 2 from the nitrite, so that's 4. And how many on the right? We have 3 from the nitrate, so that's 3. Well, so what do we have to have? We have to have 1 more on the right. So here it is. We add a water to do the job. Now, everything looks balanced except we've got to be sure about that hydrogen. Look, there are 2 hydrogens on the left. There are 2 hydrogens on the right. Guess what? Everything is now balanced. Now let's go to the other half cell. Here we have the permanganate going to manganese dioxide. Let's note the electrons again. We're going from a +7 for manganese on the left to a +4 for manganese on the right. So what are we doing? We're gaining 3 electrons. Now what's next? That's right, balance charges. So we're balancing charges, but it's in a base, so we have to use hydroxide ions. How many do we need and where? And the answer is we need 4 hydroxide ions on the right to balance the charges. What's the next step? We balance oxygen using water. There are 4 oxygens on the left. There are 6 oxygens on the right. So we need 2 waters on the left. Okay. Now how about everything else? Is it balanced? 4 hydrogens, 4 hydrogens. It appears to be balanced. Okay, now we're ready to make electrons lost and electrons gained be the same. So, to make electrons lost equal electrons gained, we've got 2 electrons lost, 3 electrons gained. No, don't think it's always going to be a 3-2 situation. It isn't. I just happened to hit a couple of good equations and that happen to have that combination of numbers. We multiply the top equation by 3, and the bottom equation we multiply by 2. That's right. That gives us 6 electrons out and 6 electrons in. So let's add them algebraically. We get 6 hydroxides in and 3 nitrites and let's see, 2 permanganates and 4 waters, giving us 3 nitrates and 2 manganese dioxides and 8 hydroxides and 3 waters. Yeah. Now what cancels? Well, the 6 hydroxides will cancel all but 2 of the hydroxides on the right. Okay, now anything else? Yeah, these 3 waters right here will cancel 3 of these waters, leaving us 1 water on the left. Okay, that's got it. Now it's balanced. Get it down. Make sure you give it the net reaction. Now, you do not want to have those extra hydroxides and waters in there. Let's move on. Actually, this is a good place to end Lecture 1. Go back and look at your notes. Pay particular attention to those steps. And then in Lecture 2, we're going to start out with a couple of really good equations to apply these steps to. A better way to teach and learn chemistry.